Today, we're really getting into it, exploring the invisible stuff that powers pretty much everything. We're talking electricity, the real bedrock principles every engineer, doesn't matter if they're civil, mechanical, whatever, has to know.
Exactly. We've pulled together some core engineering sources to give you a, let's say, a structured look at voltage, current circuits. Our aim here is to get you up to speed quickly, from the tiny subatomic flow right up to the appliances humming away in your house.
Right, quick mastery, that's the plan. And to kick things off, let's start with something maybe a bit unexpected, the definition of the ampere.
Yeah, this is fascinating. The definition of current, the ampere, or I. It's not about counting electrons, not directly anyway. It's actually based on force. The official definition from way back in 1954 is purely about physics.
Okay. How does that work?
It says an ampere is the constant current you need in two perfectly parallel wires, 1 meter apart in a vacuum, to produce this very specific tiny force between them. It's $2 times 10⁷ newtons for every meter of wire length.
Wow, okay, that is specific. And kind of complicated. Why define flow based on a magnetic force it creates? Why not just, electrons moving?
Well, because that force is the fundamental thing we're dealing with.
Yeah.
It hammers home that electricity and magnetism, they're two sides of the same coin. An engineer building a motor or figuring out power lines, they're managing that force. That definition, it's pure electromagnetism. Everything else sort of builds from there.
Okay, got it. So let's unpack what's making that force happen. We need to talk charge and flow.
Right. Back to basics. Subatomic level, you got positive protons, negative electrons, and the rule is simple. Opposites attract, likes repel.
And when we start putting numbers on that, we get the big three concepts for any electrical system, right?
That's it. First up is charge. We measure it in coulombs, you see, and 1 coulomb. It's just the total charge that zips past a point in 1 second if you have 1 ampere flowing. The key thing for engineers, though, is that charge is conserved. You don't make it or destroy it, you just move it around.
Then comes current. That's the actual rate of flow for that charge, measured in amperes A. Like if your toaster pulls 6 amps, that means 6 coulombs of charge are flowing through its heating element every single second. That's the flow doing the work.
And the third piece is what makes it flow. Voltage, V. Think of it as electrical pressure. Potential difference, or electromotive force, M, F, MEF. Lots of names. Essentially, it's the work needed to shove charge from point A to point B. The water analogy works pretty well here.
Oh, yes, the classic analogy.
Water flows because of a pressure difference, right? High pressure to low pressure, same idea with electricity. Charge flows because there's a voltage difference. High potential to low potential.
Okay, so voltage is pressure, current is flow rate. But surely if you crank up the pressure, the flow just increases. What limits it?
Good question. That's where resistance R comes in. Resistance is basically how much material fights against that flow of charge.
Yeah.
We measure it in ohms, symbolized by omega dahs. This is what engineers spend a lot of time managing, minimizing it, sometimes using it, and the thing linking all three. That's the famous Ohm's law, V equals R times I.
V equals Ri. Simple equation, huge implications. If the wire resists a lot, high R, you need way more voltage V to get the same current I through.
Precisely. And resisting flow almost always means generating heat. So a big part of electrical engineering isn't just moving power, it's doing it efficiently, trying to lose as little energy as possible to useless heat before it gets where it needs to go.
Right, so if Ohm's law is how we analyze the flow, where does the initial push the energy actually come from? The sources mention 3 main ways.
Yeah, fundamentally we get electricity from a few places. First, chemical reactions. Think batteries. And engineers talk about 2 main types here. There's the primary cell, your standard disposable alkaline battery. The chemistry goes one way. You can't recharge it.
And the ones we use daily in our phones, laptops, cars.
Those are secondary cells. You can reverse the chemical reaction by pushing current back through them. So lead-acid car batteries, 9F-seed, NaMH, lithium-ion, all secondary. And how you hook them up matters. Put batteries in series. Like in a flashlight, their voltages add up. 4 1.5-volt batteries give you 6 volts, but connect them in parallel, side by side. The voltage stays the same, but they can deliver more current together or last longer.
Okay, chemicals. What's the second source? You mentioned the sun.
Right, light. Using photoemission. 2 main ways here. You got photothermal plants, basically using sunlight to heat water, make steam, and spin a generator like a conventional power plant. But then there's the direct conversion, photovoltaic cells or solar panels. They turn sunlight straight into electricity. Materials like gallium arsenide are pretty common, and efficiencies are, around 20% these days.
And the third one, the big one, historically.
That's magnetism. This is how almost all our large-scale power plants work. You burn something coal, natural gas, use nuclear fission to make heat. That heat boils water into high-pressure steam. The steam spins a turbine, and that turbine spins a generator, which is really just a big coil of wire rotating inside a magnetic field. That motion induces the current. If you look back at, say, 2005 in the US, coal was by far the main fuel for this process.
That whole generation process, spinning coils and magnetic fields, forces a big decision right away, AC or DC.
Yeah, the great divide, direct current, DC, is simple. Like from a battery, charge flows one way, consistent. But the big problem historically was sending it long distances. You lost so much energy unless you used incredibly high voltages, which just wasn't practical or safe back then. Remember the whole Tesla versus Edison war of the currents?
Right, which is why alternating current AC took over.
Exactly. With AC, the flow reverses direction periodically. The voltage goes up, down, reverses up, down in cycles. The magic of AC is transformers. They can easily step the voltage way up for efficient long-distance transmission, then step it way down for safe use in homes. That back-and-forth speed is the frequency. Here in the US, it's 60 cycles per second, 60 hertz.
But DC isn't totally out of the picture for long distances now, is it?
No, not at all. It's interesting, actually. Developments, I think starting in the 1960s, made high-voltage DC HVDC transmission practical. For really long distances, or especially for underwater cables, HVDC can actually be more efficient than AC, so it has its niches.
Okay, so we've generated AC or DC. Now engineers need to build systems with it. They need rules to manage how it flows in complex networks.
And that brings us back to conservation laws, specifically Kirchhoff's current law. It's super fundamental. It comes straight from charge conservation. The law just says at any point where wires meet a junction or node, the total current flowing in must exactly equal the total current flowing out.
So if I've got, say, 4 wires connected, and current $I and $2 flow in,
then the current flowing out on the other wires, let's call them 3, I3, and 44, must sum up perfectly. So $I plus I22 has to equal $5 plus I42. If it didn't, charge would either be piling up at that point or vanishing into thin air, which, can't happen. For engineers designing grids or even just troubleshooting a circuit board, this law is crucial. If the currents don't balance, you know immediately there's a problem, like a short or a break somewhere.
And that current is flowing through wires, usually copper or aluminum. But even the best wire fights back a bit, right? Resistance.
It always does. A wire's resistance depends on a few things. What it's made of, that's its inherent resistivity, how long it is, how thick it is, its diameter, and even its temperature. Picking the right wire diameter is a big deal in design.
And that brings us to that weird wire sizing system, the American Wire Gauge, AWG. It seems completely backward.
It is counterintuitive. The smaller the AWG number, the bigger the wire. So like a 000's AWG wire, often called 4/0, is really thick, like your thumb maybe, whereas a 40 AWG wire is hair thin. And since thicker wire means less resistance.
The really low AWG numbers are for carrying huge currents without overheating, things like industrial machines or the main power feed into a building.
Exactly. And the tiny high AWG wires are for delicate electronics, where current is minimal. It's an inverse relationship.
Yeah.
Smaller number, bigger wire, less resistance, more current capacity.
Okay, got the wire sorted. Now, how do we connect things to the wire? There are 2 basic ways to lay out a circuit.
The first is the series circuit. Everything is connected end-to-end in a single loop. The current is the same through every component, and the total resistance is simple. Just add up all the individual resistances.
But this is the one with the fatal flaw, right? Like those old-style Christmas lights.
Precisely. The big drawback. If any one thing in that series loop fails, if a bulb burns out, a wire breaks, the entire circuit path is interrupted, everything goes dead. Nightmare fuel for troubleshooting.
Which is why our houses are wired using the other method, parallel circuits.
Right. In a parallel setup, you have multiple branches connected across the same 2 points. The key difference is the voltage is the same across every branch, but the total current from the source splits up, with some flowing down each branch. The huge advantage. If one branch fails, a light burns out in one room, the other branches are unaffected. Power still flows to the other rooms. Much more robust and practical for buildings.
Makes sense. And when you look inside a breaker box in a house, you see different circuit breakers rated for different amps. That ties back to this.
Absolutely. It shows how engineers apply these ideas. A big appliance like a central air conditioner needs a lot of current, so it gets its own dedicated circuit with thick wire, low AWG, and a high amperage breaker, maybe 50 amps. But a circuit for, say, bedroom lights and outlets needs less current, so it might use thinner wire and only need a 15 or 20 amp breaker. It's all about matching the circuit capacity to the expected load, using Ohm's law and wire properties.
Okay, let's shift from circuits to the things using the electricity. Electric motors, they're kind of the hidden workhorses, aren't they?
Totally ubiquitous. You don't always notice them, but they're humming away everywhere. Fridge compressor, microwave turntable, vacuum cleaner, fans in your computer, your car's power windows. Even if you're not an electrical engineer, chances are you'll need to specify or work with motors at some point.
And picking the right motor isn't just about speed or power, is it?
Oh, far from it.
Right.
Speed, RPM, and torque are important, sure. But engineers also weigh efficiency, cost, expected lifespan, how noisy it is, maintenance needs, lots of factors. But maybe the biggest classification, especially regarding cost and design, comes down to its duty cycle. How long is it expected to run?
Right, you mentioned two main types there.
Yeah. First is the continuous duty motor. These guys were designed to run for long stretches, like an hour or more, without needing a break. Think industrial fans, pumps, maybe the main blower in your furnace. They have to be built tougher, often with better cooling systems, to handle the heat that builds up over long operation. That makes them more complex and definitely more expensive. Heat is the enemy here.
And the alternative, for things that run just briefly.
That's the intermittent duty motor, designed for short bursts of activity followed by rest periods. Like a power drill, a blender, the motor that moves your car seat. Because they get time to cool down, they don't need the heavy-duty thermal management of a continuous motor. So they can be smaller, lighter, and crucially, much cheaper. It's a classic engineering trade-off. Continuous operation costs more in materials and design complexity.
All right, let's wrap up with maybe the most visible use of electricity. Lighting. We know lighting is a huge energy user, especially in commercial buildings. Efficiency must be key.
Absolutely critical. And to talk about lighting properly, we need a couple of specific terms. First is illumination intensity. How bright is the light hitting a surface? We often measure this in foot candles. That's 1 lumen of light spread evenly over 1 square foot. The amount you need varies hugely.
Like how much?
Well, just finding your way around a dark room might only need 5 or 10 foot candles. Standard office work, maybe 30 to 50. But if you're doing really detailed work, like assembling tiny electronics, you might need 200-foot candles or even more.
Okay, so that's brightness. But the energy side is about efficacy, right?
Exactly. Efficacy is the efficiency metric for lights. How much light output, lumens, do you get for each watt of energy you put in? Lumens per watt. And here's where we see massive differences between technologies. The old incandescent bulb, most homes still had a lot of back in, say, 2009.
Yeah, the classic Edison bulb style.
Terribly inefficient. Its efficacy is really low, maybe 10 to 17 lumens per watt. Most of the energy goes into heat, not light. And they burn out fast, 750 to 2,500 hours maybe.
How do the alternatives stack up? Fluorescence.
Much, much better. Fluorescent lamps, including the compact fluorescents, CFLs, that became popular for a while, they hit maybe 30 to 110 lumens per watt. Big jump. And they last way longer, 7,000 to 24,000 hours. So even though they cost more upfront than an incandescent.
The energy savings and longer life meant they paid for themselves.
Right. Net savings over their lifetime.
And now, the current king of the hill, LEDs.
Light-emitting diodes, yeah, they're the game changer. Super long life, often quoted around 20,000 hours, maybe much more now. They use way less power for the same brightness and run much cooler. The potential savings are just staggering. The U.S. Department of Energy figured that if LEDs became widespread by 2027, the country could save something like 350 billion kilowatt hours of electricity.
350 billion kilowatt. It's hard to wrap your head around. What's that comparable to?
Let's see. That's roughly the amount of electricity needed to power every single home in a state like New York for like 2 full years, just from changing light bulbs. It shows how much impact improving the efficiency of one simple, ubiquitous component can have.
Incredible. Okay, one last lighting thing, that weird color temperature scale that always trips people up.
Yeah, Kelvin. It is totally backward from how we usually talk about color temperature. It's measured in Kelvin. Okay, high Kelvin numbers, say 3,600 K up to maybe 5,500 K, are called cool light. They look sort of bluish white, maybe a bit greenish, often used for task lighting or in stores. But the low Kelvin temperatures, down around 2,700 K to 3,000 K, those are called warm light. They give off that yellowish red glow we associate with traditional bulbs.
So high temperature number means cool color, low number means warm color. Got it.
Exactly. Warm light generally feels more relaxing, so it's preferred for homes. Cool light feels more alert, better for workspaces.
Okay. What a journey today. We've really traced electricity from that super precise magnetic definition of the ampere all the way through the rules like Kirchhoff's law that govern flow and into the actual things engineers design, the wires, the circuits, the motors, the lights that shape our world.
Yeah, we saw how it's all about managing fundamentals. Resistance and wires, the pros and cons of series versus parallel, picking a motor based on heat and runtime. And we touched on that massive potential energy saving from LEDs, that 350 billion kilowatt hour figure. It's huge. Which makes you think, if just improving the light bulb can do that, what's the next component? What other maybe hidden super efficient thing, a capacitor, a different motor type, a new material is lurking in our devices right now? What's poised to create the next massive energy shift? Often, the biggest engineering wins come from optimizing those tiny, seemingly mundane parts. Something to ponder.